Yeah, very welcome. To this bootcamp. To participate in is a deliberate attempt to create India's top AI talent. So, um, at the AI Institute at University of South Carolina, uh, and before that, I graduated. I've supervised 48 PhD students, and those who have graduated have gotten some of the best jobs that are there, competing with graduates from Stanford and Berkeley and CMU and all the places. Some of the people are trained, and they are at other top places like MIT Media Labs. They are faculty. They develop very good companies, startups, and they are in industry in very high positions. One of the reasons I started IRO in this February was my meeting with the Prime Minister of India in December 2023. He had invited to meet with him. We had one-on-one chat. Then he asked me to give a keynote to Niti Aayog's Chief Secretary's conference, where government's top bureaucrats, IS officers were there. And eventually they took the shape of this with four objectives of IRO. You can see this IRO. And Hey, there's some people waiting, so you might want to admit them. They need
Hey,
to really start early. But so the IRO has four objectives. One is to create India's very top talent. So we're not talking about a student at IIT or BITS or something. We want to create students that can compete with the best in the world, in China, from China, and in US and such. Uh, how would you know that we are trained the best? Well, average citation of my PhD student before they graduate has been 500, and one third of have citations of more than 1,000 before before they graduate, right? So, and most of them, they publish between 25 and 40 publications before they graduate and do a lot of other exciting things. So there was a deliberate, there was an ecosystem building effort we call Gurukul that led to creation of such high-end talent. In last few years, I had a lot of Indian students who did virtual internship with me, and then some in person, and they went on to do great things. So the core talent has been there in India always, but Indians always had to go to US or some other places to get their masters and PhD and be successful. For example, Arvind Srinivas in Berkeley, and then he worked for OpenAI, Google, uh, and DeepMind, and then he started Perplexity. Right, that ecosystem environment in which you get training for the world's best has been lacking in India. So IRO is the effort to really create that. In addition to that, we are creating sovereign AI, meaning original AI technology, and we are enabling startup and their products, and we are building national applications. But the most important thing is the talent creation, top end talent creation. Since some of you come from our partner organizations like IIT Gandhinagar, BITS Pilani, um, that or I met your uh, uh, professor, let's say at IIT Kanpur, we invited, most of you are nominated, and so invited some of the best there are in India. And we want to give you some snapshot of significant AI work that is novel. So we are not going to teach you things that you can routinely find on YouTube. We do not want to teach you to create a small language model, YouTube videos. And this is going to be hands-on. This is going to require hard work, and we are going to do our best to expose you to new things. Let me start with a little AI. there is a
Dr.
there is a
Sheth,
LinkedIn page. You should consult news about activities and innovations and other things at IRO. Uh, you would this is from Anna. You all have seen. Let me start with the video that was just posted today. This video is by Dr. Sri is a Padma Bhushan, co-founder of SCL Technology and current chairman of India's quantum mission. Let's see what he has to say.
Will come up for different areas.
Venkat, do you need me to stop my screen share?
For education, something for
Yeah.
climate,
Sure.
all kinds of SLMs will be there. And these are going to be made in India. Okay? They are going to be our own. I'm involved with a research institute that's just been set up at Gift City in Gujarat, where we have brought some Indians back from the US to get it started. And the whole strategy was that the AI mission, the Gujarat government, and the Pharma Association, we all got together and put together a 300 crore budget by which this AI Research Institute could be started. And the whole objective of this AI Research Institute is to create SLMs for India so that we can actually solve problems of India. Really, the real application of AI will come through small language models, SLMs.
Okay.
So SLM.
So we are fine. And now let me. So guys, there was this discussion on SLM, but I want to make some specific some unique points. So you are really not going to be limited to what is traditionally called small language model. We are going to look at some advanced version of what is broadly called small language models, but in reality, we are going to go beyond that. The small language model through known techniques like quantization, like distillation and all, these are well known. And they are trying to do on a small footprint what the large models do. But we are going to do something that is going to be functionally different, right? And its capacity is going to be quite different. So what we are going to do is, this West and China are way ahead than India on LLMs, but they are for largely consuming, for consumers. The models that we are creating, the next generation of models we are creating, are for typically solving very specific problems. So, for example, I hear a list of a few of these examples: healthcare and clinical care, infrastructure and sustainability, like weather and climate and others, power grid, pharmaceutical, R&D, semiconductor manufacturing, right? These are clean power generation, like solar power plants, windmills, right? Or manufacturing, like automotive manufacturing. The idea here is that they don't need LLMs per se. They don't need models trained on everything that you can find on the internet, including the material that you don't own, pirated information. They need to be trained on their own data and the knowledge of their domain. So one of the things, consistent thing you'll see in our presentation is that data alone is not enough. The models are created when you're creating a parametric space by learning from data using transformer or some other architecture. You are getting basically a statistical information from data. We believe that you can do much better by having knowledge. And by having that knowledge, you can build systems that are more intelligent, that are more robust, and they are more trustworthy. These are the kind of things that enterprises want. These are the things that you need for making a system that you can depend on. So there is a saying that if you are right 95% of the time, you're fine in consumer market. But with 5% errors, you are dead in water if you're doing enterprise application. An enterprise can't accept 5% errors, right? But the current models that you use have a lot of errors that you are not aware of. They look very suave, they look very human-like. But in reality, factually, hallucination and other things make them highly unreliable. So here I define 14 different what we call as foundational elements. And these are the kind of things that are very important for real world application. Take an example of alignment. Recently, so suppose you are using in clinical care, and if you do not follow the clinical protocol or standard or guideline, you are in deep trouble. A doctor is supposed to follow that, right? So you have to follow those aspects of that domain. In this case, I gave you the example healthcare, but suppose in financial domain you will have regulations. In pharmaceuticals you have regulations. Those must be followed. Can you make that follow? Can you follow them reliably in an LLM? Yes, you can build a RAG, but that's really not a good solution. Okay, so we are talking about an entirely new class of models that in which we think that there is a massive amount of requirement because they are domain specific, they are problem specific, they are task specific, they are very high value, right? And there's a lot of need for them. And the expertise for them is available in very small, very, very few people are available who can train this model from scratch on your own data, enterprise's own data and the knowledge for that domain, right? That is what you're going to be exposed to. Of course, in 5-6 weeks, you're only going to still scratch surface. But this is the class of models we are doing. Recently, there was a case where a farmer used large language model to choose spraying of pesticide. Well, he killed all his crop. This is the problem, right? So you really have to create solutions that are highly specific to that particular problem and task at hand, right? To give you an example, we are currently building a model for maintenance of a 500 megawatt power plant. I hope you are getting a sense of what we are trying to do, right? So now in doing so, for example, there is a area here called explainability. To explain how the AI system came to a particular decision and recommendation to a user in enterprise, you really have to train with the knowledge of that particular domain. If you don't, you can't explain in that particular term, right? There's a word called edema in medical context, and its meaning is retention of bodily fluid. How would an AI system understand clearly when mention of bodily fluid maps to edema for the doctor when you explain to the doctor, right? So anyway, I have a lot to say, but I'm not going to say a lot more here. You will understand by your own expertise. Let me see if and there are different aspects. I'll just show you one thing. So last item is neurosymbolic, right? Let me show you just one little thing. So let me see. This is a wiki page for the AI Institute, and there is this project called Neurosymbolic AI. And what you will go and do and see is that there are 11 PhD students who have worked on something related to this area, and literally tens of publications in top conferences and journals and all that. These are all dissertations are here, their videos are there. But it is this kind of original research and what I would claim to be the world leading research in this area that goes in the what we are going to try to expose you to some extent. Okay, so I will stop here. There is a lot I can say. Obviously, as professor, I can always say, go on and go on. But let us stop here, and I'm going to turn it over. If somebody has a burning question, go ahead and ask. But otherwise, we'll like to move, quickly. Anybody has a burning question? Okay, so we are going to try and take you through a journey on things that are not routinely available, that are you're not going to find in a YouTube video, all the things that we have. Of course, we are going to have to start with some basic things that, of course, you can find easily online, and then go hopefully to the more hands-on and advanced thing. In the end, let me help you understand something. Suppose you know RAG. Suppose you know fine tuning. Suppose you know how to use LLM. Imagine what kind of jobs you can get. You probably can get job in an IT industry. Suppose you know how to create a model, and not only language model. It can be AI model with sensor data, with images, with video. And you know creation of this model from scratch, from first principle. What kind of job you can get? How much value you would have? The two has no comparison. So IRO is not about creating skills. You can get that from your courses. You can get that from YouTube. You can get many, many online things you can learn from. What we are going to try and get you is to get a sense of really challenging and beyond state-of-the-art research-driven AI. So hopefully you'll pay very strong attention, participate with a lot of dedication, and you'll get a lot more. Okay. There are some prices and all. For example, a couple of you might be invited to spend a month at IRO with expenses paid, and there are some other things that we will do for some people that are very that should to be very capable. And also, I mean, you may get to interact with some of the IRO research scholars and pre-docs and postdocs and assistant, and they are amazing group of very, very, very talented, some of the best young talent that we have in India. And so you can get to interact with them and see, and you can aspire to, you can first do online internship with us, and then if you are really well and show the promise, maybe one or two of you might be invited to do in-person internship. So with that, I turn over to the team who is teaching this course.
Thank you, Dr. Sheth. Over to you now, Keshav.
Sure, thank you. I'll just start my share again. Is it visible?
Just coming up. Yep, we are now able to see it.
Okay. Hi, good evening, everyone. So thank you for the great introduction, Dr. Sheth and Venkat as well. This is the first lecture in the Pramana SLM++ lecture series. Today, we'll be covering sort of an introduction to the course, why SLMs, what SLMs are, setting some of the baselines for training these models like deep learning, PyTorch, and what kind of engineering hacks that often are going into these problems. And also introducing a new concept called OLM, which is a library for training SLMs and LLMs at large. We'll be diving into a few technical details as well, but mostly this lecture will serve as a base, a grounding, and it'll set the foundations for what you guys will pursue in further lectures. We're partnered with all these sponsors, as you can see: Department of Science and Technology and Government of Gujarat, India AI, ANRF, the Ministry of Electronics and Information Technology, AISC, as Dr. Sheth mentioned, Ahmedabad University, and NVIDIA. A quick introduction over myself. I am Keshav Prasad. I'm currently a student at Plaksha University, and I'm an intern at AI Institute of University of South Carolina. And I'm the co-creator and open source maintainer of Open Language Model, which is one of the frameworks that we will be studying in this course. And currently, I'm working to build enterprise-ready sovereign SLMs for IRO for food and nutrition. everything in this session that we will be discussing today is the same stack being used in IRO and in other endeavors. So we'll be covering things that are being used in real life in real time. A quick overview of the session agenda. Basically, this will be around a 2-hour lecture. We'll try to keep it as crisp as possible and try to keep it as as high engagement as possible. We'll understand why SLMs and why this is more of an economics problem and not a mathematical one. Then we'll understand why making SLMs is an engineering effort and what are the kind of engineering pursuits we have to take to get to these levels. We'll go through a lot of things like mixed precision, torch.compile, gradient checkpointing, and OLM. And then we'll see a live demonstration of all of these things running and see all of the things that we discussed in theory, how do they work in practice and in code. And then we'll take a few questions. None of this is extremely complicated. This is all setting a foundational level stuff. So it's very possible that a lot of you are quite well versed in this, but at least what we'll try to do today is try to give you a perspective on SLMs and try to give you a perspective on using these specific models as parts of a larger system when making SLMs or when making real world solutions to problems using an SLM perspective. Excuse me. So by the end of this lecture, you should be able to defend 3 claims. You should be able to explain why we specialize, why we use SLMs, why we use focus models. You should be able to understand the fact that SLM training is economics, why we pick SLMs, what data we use, what model methods we use, why it's an economics issue. And 3, judge the trade-off, where we try to sort of break the philosophy that we have that training SLMs is tough because it's tough to understand the math or calculus, but rather we want to understand that it's bound by memory or GPU compute or the kind of operations we're using or the data we're using. Okay, so it's very important to understand before we dive into the rest of this lecture and the rest of this course that why are we discussing SLMs? This is the age of LLMs. We have lots of giant models available for free, open source, or using API credits. Why should we focus on SLMs? Dr. Shade covered this a bit in his introductory session, but I'll give a quick overview as well. A general model is broad and shallow, as in you might be considering large language models like ChatGPT, Gemini, Claude. These are in general very, very broad models. They cover a very wide variety of topics, but rather they are shallow for each of these. They're able to cover sort of a minimum criteria of intelligence for each of these topics, but they sort of fail to specify in any of them. If we have a task-specific model, a specialized model, it is narrow. It covers one domain, but it is deep. It is able to create more knowledge. It is able to create more operations, and it is overall a better performer for that one domain as compared to a general model, which would be shallower at that domain. Hence, we want the right model, not the biggest one. Yeah. So again, an important question is why would we not just call ChatGPT, right? Why would we not just call on a larger model? Again, these models are excellent tools, but there's a lot of things to be considered. There are 3 very real constraints that we study while using these models for actual application-based purposes. Number 1, obviously, cost per call, latency budgets, and throughput ceilings. All models which are not sovereign, you cannot control these, and hence they become an unseen expenditure or an unseen constraint on your operations. Privacy, regulatory constraints, and workloads, all of these are very important for creating sovereign models. Like Dr. Sheikh was mentioning, if you want to create models that are sovereign, then you can't consider certain operations that are hidden behind paywalls or privacy constraints. And again, that we considered the depth versus coverage area. Is there a lot of fine-grained control? Is there a lot of deep control over a model if we use large language models that are publicly available? So what exactly is an SLM? An SLM stands for a small language model or a specialized language model. It is a model optimized for a specific problem domain rather than for general intelligence. We try to define SLM through 3 main tenets, which is focused, cheaper, and better. An SLM covers a focus problem. It is covering a specific domain rather than trying to cover a very large set of domains. So it's focused on a smaller problem. It is cheaper because it is smaller, less compute to train, less to serve, and even smaller to deploy. So it conserves a lot of the costs of memory overhead with large language models. And it is better. For a specific domain, we can get a higher accuracy, higher performance, and higher usage out of a SLM for that's compared to a large language model. For a simple one-liner, we can use SLMs when we have one domain, a tight budget, and we want to deploy on localized hardware. You might be wondering why this is called the SLM plus bootcamp. Why not just the SLM bootcamp? And it sort of goes into what Dr. Shit was talking about. That has been the philosophy of IRO and sort of should be going ahead is the C3AN framework that was developed. The C3N stands for custom, compact, composite, and neurosymbolic. Custom stands for domain specific data. Basically, we are able to define what workflows we're working with, what data we're working with, and what constraints we're working with. Compact is that we are not prioritizing scale over operation. So we are able to create reliable domain adaptation without extreme scale. This is what we'll sort of be diving into today. And composite means that we are able to combine a lot of expert models into one system, and we're able to create neurosymbolic system where a neural symbol and symbolic systems join together to get the benefits of both to create a SLM which has a higher capabilities than one without. Another important part that we sort of want to stress on that we will, of course, dive further into in further lectures is knowledge graphs. Knowledge graphs is a very powerful tool. We have a lot of models like SLMs, and LLMs and transformer-based models. So far, they learn patterns. Knowledge graphs hold facts. It is very interesting. It's a very interesting measure that a lot of companies like Anthropic and OpenAI have done a lot of research in trying to do interpretability work basically on SLMs and LLMs and try to isolate the neurons and figure out how they can change the rules of a model, make it editable, change a few facts, etc. And it's been an extremely laboring task. Merging with knowledge graphs makes this task much, much simpler and much easier and much better. So knowledge graphs, it's very easy to change the rule by editing the graph, and it makes explainability and auditability much, much easier. You can answer, instead of asking an LLM why and it retraces through a call stack, you can simply trace back through a path on the graph and figure out how we got to this problem. It is knowledge graphs are widely being used in pharma, healthcare, and manufacturing, and they have been used in IRO's efforts as well to create sovereign SLMs. Again, this is going into the similar thing that Dr. Shape was mentioning, which is the C3AN paper. It defines 14 pillars across three main criteria, which is intelligent, robust, and trustworthy. And we're understanding why we should prioritize SLMs, or rather SLM++, than monolithic LMs. We can judge them basically on where knowledge lives, how we can change one rule, explaining an answer, and what the models are judged on. I encourage you to dive further into this paper, read into it, and try to understand the perspective that is built around building SLMs and what is the direction this group is taking SLM building towards. Yeah, moving on. So let's dive into the main portion of the lecture. Understand the economics of AI. Sure, it's very important to understand. Okay, smaller and specialized models, they always sound nice. It's very interesting and it's very easy to think about them. But often it's difficult to understand why it is forced on us. Everything we do costs compute and memory. This statement might seem very simplistic or repetitive or rather rhetoric, but it's very important to understand that this is sort of what governs the entire SLM training process. The goal for this lecture as well is to sort of give you a perspective, to create a mindset shift before we go into actually training models and understanding how each portion of that works, is understanding what is the perspective that we should be approaching every step with. Every training second, every gigabyte of VRAM, every GPU hour, everything costs compute. So everything costs compute and memory, sorry. And these compute and memory gets translated directly into budget. So everything boils down to the economics of the problem. This is why when we have a lower budget, we can train smaller models because we are bounded on compute and memory. Hence, we have to prioritize finding better solutions and better tricks to make lower budget training more efficient. So this boils back to the things we were discussing before. focused, cheaper, better. This is a solution to our problem of a lower budget. We are able to answer the problem that we just defined. That basically means that we narrow the problem, spend less on it, but in a smarter way, so the result gets better. Again, you might be asking, why are we starting here instead of transformers or tokenization as any other standard SLM building or LLM building or language modeling course often does? But I think it's very important to understand the perspective that we're trying to put towards. Every lecture that you guys will take further on, every different topic, every different portion of the workflow of the pipeline of SLM training is a different way of spending or saving the budget that we just defined. Without that, there are techniques with no reason attached. You might be understanding, well, why are we doing tokenizing in such a way when we could just put more compute, more memory into it, and have it be done in a more complete fashion? But again, that would be answered by understanding the perspective that we take towards building SLMs. Is that why we specialize, what training actually costs, and what we spend it on? Understanding the economics of artificial intelligence. We'll also, so to understand this visually and to keep track of it, we'll create something called the cost line. Today, while we'll study every single technique in a sort of overarching fashion, we'll understand what it costs. Either it'll cost something in compute or it'll cost something in memory. Compute basically means the money it takes to run a GPU, sort of in power, GPU in power or in electricity or something like that. And the money it takes to run a GPU in compute. And memory means the money it takes to store something in memory. Every technique right now that we'll study tonight or further on in any of the lectures will either spend one of these currencies or save it. This will help you get an understanding of what method we're taking. We'll slowly build up a lot of operations that are necessary that will increase the cost line. And then we'll try to do a lot of hacks, a lot of tricks, and a lot of engineering methods to bring these costs down and make it cheaper, focused, and better. So let's break down the problem. We all know that we all are quite aware that model training is all the rage right now, but why is it difficult? Why is it a problem? And also, why is it so expensive? We have very large figures that training models, even SLMs, cost tens of thousands of dollars to hundreds of thousands of dollars to even millions of dollars. To understand why model training becomes so expensive and so difficult, well, let's break down the problem. The bottleneck is rarely the maths, as you may have assumed. It is not that the maths is too complicated or the weights are too large. It is usually constrained by systems and not the calculus that drives the system behind them. Like we studied, we can study three main bottlenecks. Number one is the memory. The model, the gradients, activations, all of these terms may sound unfamiliar, or if they are familiar, well and good. If they are unfamiliar, do not worry. This lecture will introduce more questions than it will do answers. And that's better because we'll be diving into a lot of the answers for those questions that you have in further lectures. Right. So memory is a big issue. All of these model gradients activations have to fit somewhere, either on local machines or on some memory stacks or servers, etc. Bandwidth and storage. This is also something we'll dive deeply into. Is that oftentimes it's not just computing on the data that's a problem, but rather moving the data from one location to another where it is being computed on. That causes issues. This is a very common problem in a lot of different systems. The bandwidth of data transfer is a bottleneck. Throughput is also a very important context. Throughput basically means, you might have heard of input and output. Throughput just means the data and operations that is happening in between. One that doesn't enter in and one that doesn't go out, but the operations that is done by the system in the middle. This is usually something that is, like similarized to GPU, that is constrained with GPU compute. The better your GPU is, the more compute you have, the faster your throughput is. It is not entirely so simplistic, but rather that is sort of the approach that we take to it. This is a simple diagram of the pipeline. We will be studying this entire pipeline throughout this course and well beyond this pipeline as well. But this basically shows every stage of training. We take raw text, we tokenize it, we turn embeddings, we create a transformer, we do pre-training, we do fine-tuning, we evaluate, and then we deploy. The pre-training and fine-tuning steps are the steps where 99% of the compute and memory are actually spent. This is the part that we need to figure out where is the money that we are spending on training these SLMs going, and how we can make it better and faster. We will also have a lecture further on cost accounting for LLMs, and we will dive further into the each and every single memory operation. But today we'll sort of study the establishing of the problem of the why the for which the solution is SLM training, and how we arrive to it. So let's see how we can solve the problem. We'll take a three tier approach. First thing we'll do, we'll express the work, which is deep learning. PyTorch, CUDA, GPU, all of these things. What is the computation? Where is it written down? And where it actually runs? Secondly, we'll try to make it fit. You have a certain memory given to you, allotted to you, and you have to try to make the model fit. Autograd, mixed precision, checkpointing, all of these things are engineering decisions to try to make a model fit in a given memory style. And the third is to make it fast. Torch, compile, and profiling. So these are sort of methods to make model training faster. These aren't just methods to reduce compute and memory, but we'll also try to make it so that it's a more focused effort and time effective as well. Let's first dive into the work, which is deep learning. In this section, we'll sort of study the computation graph, autograd, and the memory and compute they both secretly demand. As you might be aware, if you've done certain levels of deep learning before or machine learning before, a network or a model or a neural network is just composed functions. One function operates on an input, and the output of that is operated by another function, and similarly, so on and so forth, very similar to an assembly line. A couple of hands keep operating on the same input to convert it into an output. This is very similar to how LLMs work as well on a much larger dimension. Today, we're not asking what F1, F2, or F3 or any of these functions compute, how they compute. We'll just study that they are there and they cost something. And every function call like this runs on the GPU, which is a real non-zero cost. As you can see, the cost line has now extended. This is what we call compute. We have spent some compute, and hence our cost has gone up. This is defining something called the forward pass of a function. This is when we take an input and create an output. That costs money. Very simply, that costs compute. Learning those functions how to approach the right input-output pair for each input is a very common problem which started the entire industry of machine learning, and it was solved with something known as gradient descent, as I'm sure you're all aware. Naively, gradient descent, how it works is it uses calculus to figure out how much each weight affected the output. The simple way to run it would be change one parameter and rerun the whole forward pass and see what changed, to judge how that one parameter changed the output. Be very similar to resolving an entire maze from scratch just to check one wall. It becomes redundant and it becomes too costly. Like you see, the naive cost scales with the number of parameters. 1 billion parameters, as is a lower level now on SLMs as well, means 1 billion forward passes for one gradient step. That is simply not feasible for understanding how, training models in an actual world. What actually happens is something known as autograd. Autograd basically builds a backward graph of the forward pass live as the forward pass is happening. We'll observe this further when we do the live demonstration. It'll be much easier to understand. But from a theoretical standpoint, every single time an operation is called on any variable, we build a backward graph consisting what is the operation that causes output, and then what is the derivative of that operation going backward. For example, like we see, then x and y are being multiplied. So here to create an output. So the derivative would be the opposite direction. For example, the output xy, their derivative with respect to x would be y. And the output xy with respect to the y, their derivative would be x. So this builds a backward graph, a computational graph as a forward pass is happening. So when doing gradient descent, we don't have to nudge each parameter and do forward passes. We just have to walk the computational graph backwards in reverse, producing each gradient for each step in the operation. This was one of the biggest discoveries in deep learning. It removed the biggest barrier, as I'm sure you're all aware. And but it did not come with no cost. As you can see, AutoGrad needs two things: compute and the memory to hold these activations and this computational graph. Hence, the cost line is extended again. Next, let's go on to the making it fit portion. We have covered the very basic hierarchical overview of how any deep learning model is trained. There is a forward pass that is defined by a certain set of operations, certain functions coming together. And there is a backward pass that is defined with a computational graph built and traversed backwards every single time gradient descent has to be done. There is a lot of different things that we can go down further into this, that this lecture series will go into. There's a lot of portions that it might not, because they remain outside the scope. But this sets the overall ground for understanding how deep learning and hence SLM training works. A GPU has thousands of cores and huge bandwidths. Why can't we train SLMs on laptop GPUs, on any other GPUs that are present? What is the major bandwidth holding us back? This sort of question remains a black box very often, where we don't assume why we are not able to do something, rather than assuming it is just in place of assuming it is a difficult task. It's very important to break down why we are not able to do something so that we can figure out the ways to make it happen. So let's figure out the problem. What is the problem? Why are we not able to train this on small GPUs? What you might be thinking, well, weights, the numbers of the actual weights there are a billion parameters or so. That's a lot of data to be stored somewhere. Yes, that is correct. But that isn't the entire story. We just built something called the computational graph. In that, a graph is stored where each operation's output, each step of the function, their output, also known as the activation of that output on a neuron, is stored. These activations often dominate GPU memory. As you can see in a 1.3 billion parameter model, weights are only 5.2 gigabytes, gradients are 5.2 gigabytes, and optimizer states are 10.5 gigabytes. Whereas activations, when you do it naively, are 91.8 gigabytes. This becomes an accounting problem. Memory dominates. You have to have a lot of memory just to store these activations. As is visible on the cost line, the activations being stored expand the memory cost so much that it becomes infeasible to continue in this way. What's the solution to this? The solution to this is fixing how we store these numbers. Diving into how we store these numbers is a very important aspect, because the data has every data has a data type. Very often we consider in model training and deep learning the floating point 32, which has 32 bits, 1 sign, 8 exponents, and 23 bits for fraction. These models, which when stored in FP32, are described as 91.8 gigabytes. This becomes infeasible. To solve this problem, another sort of data type was considered, something known as bfloat16. In this, it has 1 bit for sign, 8 bits for the exponents, and 7 bits for the fraction. Let's understand what this means. When studying any data type, we can consider two things: the mantissa and the exponent. The exponent is obviously the exponent defined here, which is 8 bits for both. The exponent stands for the zoom level. How large and how small are the numbers that we are storing? How large and small can they actually get? The mantissa is very similar to a resolution. How precise are we storing these values? This is considered by the fraction given in these bits. FP32 has 23 bits put aside for fraction. The bfloat16 has 7 bits put aside for fraction. We can see, yes, there's a considerable loss in resolution. But since the exponent is the same, they have the same zoom. This works in a lot of different scenarios, because in a lot of different locations, we don't need to store numbers very precisely. However, we do need to store them in their zoom. For example, if we're only able to store numbers up to 1 million, then any values above that would boil down to nothing, will boil down back to 1 million. However, if we're able to store a very, very large range of values, but only in a specified resolution, then we will lose certain data for sure, but we will be losing it less because then it becomes interpolated data. A vanished value deletes information. A rounded value adds noise that the network already tolerates. This intuitively and mathematically halves what we store. This using bfloat doesn't touch the compute because the compute operation is still the same. It saves memory. We are storing numbers, but storing each number costs less because each number now is smaller in data. We can study this as well. So in FP32, each number takes 4 bytes. BF16 takes 2. That is half the memory. The range is exactly the same. The precision is lower. This adds noise, but the network absorbs this noise. This costs us slight precision, which network is able to absorb. What does mixed precision mean? You might have heard this term before when you're being used in models and in training as well. Mixed precision is what came alongside BF16. Like we studied before, that using BF16 adds noise. There's a lot of parts in a network that can't drift, that can't afford these noise, like master weights, optimizer states, gradient reduction and normalizations, stuff like these. These rely very deeply on the finer digits of the fraction. Hence, using a BF16 there would cause lack in accuracy, would cause lack in performance, etc. But however, there are certain parts in a model, certain data points, which don't need to be that precise. Things like forward pass activations, matrix multiplies, which is most of the operations of a neural net, of an SLM. The matrix multiplies, they don't need that much zoom because the noise introduced there is already absorbed by the network. Hence came the idea of mixed precision. Certain spaces have numbers stored in FP32 and certain spaces have numbers stored in BF16. This retains the accuracy and performance by putting in the precision again where it was necessary, and still saves us a lot of memory by reducing some of that precision in place of noise where the model can afford to do that. We can study how much this costs. We'll study this as well when we do the live demonstration. But without BF16, using just FP32, a large language model with 256 embedding dimensions, 6 layers and 4 heads. All of these words will start to make more and more sense as the lecture series goes on, I understand. But this stored was around 69.6 megabytes on machine. When using BF16 and mixed precision, they cost 34.8 megabytes. They're exactly 2 times smaller in using BF16, which mathematically makes sense since the bytes are exactly half. In practice, this number might be smaller since we're using mixed precision, but again, any memory saved is better because it is cost saved. This represents the first engineering trick that we have to make the model fit on the hardware that we have. Secondly, we have to understand that storing activations is also a big challenge. Like we studied in the beginning, activations often dominate the memory that we are storing on card. The first fix that we did is make storing every number cheaper. Now we have to understand, do we really need to store all of these activations? What are they for? When we built AutoGrad, we understood that a computational graph requires the output of each function, also known as the activation, so that backpropagation or gradient descent can happen cleanly without billions of forward passes. This requires the activation of each of the outputs of each function in a very large model, which often has billions of functions. Storing all of those outputs is what causes a large memory. What a very common trick to preserve this memory is known as gradient checkpointing, or also known as activation checkpointing to be considered. What we do is, instead of storing all activations, we store every nth activation and rebuild each of the activation from that point forward. You might be thinking, well, this boils down to the same thing as naive gradient descent again. If we don't store the activation, then we have to do a forward pass again, recalculate everything. That's just That's just coming back to the same problem that we thought we solved. However, we can approach something known as a middle ground. Here with checkpointing, we're not removing all checkpoints, neither are we storing all of them. Storing every NS checkpoint creates something known as a trade-off. We trade a little bit of compute, we do a little bit more of operation to save a lot of memory. Here we save in this specific operation with just 12 checkpoints, we're able to add only 25% more compute while saving about 10 times of memory. In a lot of situations, the compute we have is abundant and the memory is scarce. This is a very important trade-off that we can do to trade the cost that we are using from memory back to the compute. As you can see from the cost line, the checkpointing has added a little bit of compute, but it has saved a lot of memory. So we've covered quite a few things in a sort of very quick span. So let's stop for a minute and take any questions that you guys have. We'll spend 5 minutes on this and then we'll go on further.
I had a question.
Yeah.
So voice is very feeble. If you can speak up.
Yeah, am I audible now?
Yes.
So the point where checkpointing is used, does it also involve using mixed precision over there? The FP32 versus BF16?
Yes. So again, both of these measures sort of come together. Gradient checkpointing that we studied, we have mixed precision describes that certain data types are used in certain spaces. BF16 is used for forward pass activations here, right? So when we store these activations here, we are storing them in BF16. So both of these tricks combine together to save memory and compute.
Okay.
Hello, am I audible?
Yes.
Yeah, so when we are doing the nth checkpointing, are those nth locations predetermined, or do we need to use additional compute to even find out which positions to actually checkpoint at?
That's a very interesting question. In a lot of the systems that we do practically, they are predetermined. But I'm sure there's been a lot of research in trying to figure out which positions are selected, why they're selected, and I'll encourage you to look into that. Or further, we'll get back to you on if we have any further information for that. But in practice, they are predetermined.
And Keshav, like we have a question in the chat line, Paul. So basically, what an SLM is a type of model that is built for a specific domain.
Yes, an SLM in a very large generalistic perspective is a model that is built smaller and more precise for a specific domain. Mixture of
No,
experts.
SLMs are also built that are not specific to domain. I mean, for example, many of these guys who create large language models, they provide also smaller models. Say Gamma, so Microsoft, so also the Google. Now, Phi from Microsoft. So making it smaller for general purpose is also possible and appropriate. Here in our case, if you heard what I said earlier, we are talking about multiple different topics. One is custom. Custom is typically for a specific task, but the task may belong to specific industry or industry sector. Let's say pharma. So then you could choose to make pharma specific model. Even within the pharma, there is a drug repurposing versus drug discovery, or there will be some other pharma expertise like regulatory tasks like regulatory compliance. So there would be a potentially different domain specific and star specific models that you can create. So you have arbitrary choice. But the point is that you could have simply taken a large model and applied various techniques to make them smaller with the minimal loss of quality. There will be some, but minimal, and hence get an overall benefit. That is one thing about just creating small model. But we are talking about small models that solve specific problems, so custom models. And we may even want to say we want to deploy this model on the factory floor, or you want to deploy this model on on mobile phone, right? A model for farmer can be on a smartphone, as an example. So in that case, we may keep all those in consideration. That's why what you heard about overall cost consideration, we need to understand all of those aspects. More importantly, we want to emphasize that when you create a small or targeted model, in fact, the word I prefer to use is compact, for a custom problem, specific problem, you also not only talk about developing model for a domain, but we want to bring in the domain knowledge. So for example, in our pharma related model, we create pharma knowledge graph, extensive knowledge. For example, we could extract knowledge from medical literature, or we could extract knowledge about clinical guidelines in managing asthma, right? And then those knowledge also would bring into creating the specialized model, and you will hear about it later on. So there are multiple aspects of it: custom, compact, neurosymbolic, and composite. And you'll get to hear, you get more details about each of them as we proceed, to some extent at least. Sorry, long question, answer to a question.
Yeah, just a question, sir. So I think the whole basis of GPU architecture was we deviated from Von Neumann, Harvard. Is that because this is on a heavy computing side versus the data movement side, right? So keeping that in view, we little contradicted that statement. Am I with you? I mean, for that, yeah.
Keshav, go ahead. If you understood the question.
Did I make my question clear? Yeah.
I'm sorry. Could you just clarify again? I'm a little.
No, I mean the very essence that GPU architectures came is that like to help build the computing side of the processor, not on the data movement side. Whereas to just take a generic CPU architecture, it's good on the data movement side. Whereas here, like that statement, little off from what it's meant for, right? I mean, am I with you with that? Yeah.
Yeah, absolutely. I think it's a perfectly correct statement to say that modern GPU architectures prioritize compute over memory data transfer bandwidth, and that is why I think we're able to say a lot of times that compute is abundant and bandwidth is scarce. That's also why I think GPUs are used in a lot of other operations other than computation, where operations are prioritized rather than memory transfer.
Still, I presume we'll be running these SLMs and graphs on the GPUs, right? Yeah.
Yes.
Okay. Oh, fine.
Okay. Should we move ahead?
Yeah.
Sure. I have a question. What happens when the checkpoints that we have that they do not match to the activations that we calculate again? So repeat the process, or?
So what will happen is the checkpoints that we are storing are deterministic. So a model in general, before training, is deterministic. So whatever framework you're using will raise a runtime error, because on a forward operation, and when we're building the backward graph, we store certain checkpoints of the outputs. When we're rebuilding from those outputs, each checkpoint should match with its outputs to the next checkpoint, because the weights haven't been changed from when the activations were computed. So if there's an issue, then the computation graph is broken somewhere, or certain issues have arisen in the operations procedure.
Got it. Thanks.
Should we move ahead?
So there is one question in the chat line. Okay, so somebody wants to go off.
I think we'll have to move on, otherwise we'll not finish. It's a bit very late for people.
Sure. We'll move ahead. Yeah.
Sounds good. So probably like we are also very close to the break also, right? 9:45 to 7:15. probably you can just give an introduction about something, and then Keshav, and then we can have about 5 to 10 minutes depending upon how much the content you wanted to deliver. So just probably we can break for 5 to 10 minutes after 5
Sure.
minutes. Yeah, sure.
Sure. Okay. So we've covered two main portions of the problem that we were studying today. We have defined the problem and we have tried to make it fit. The the third portion that we're studying is making it faster. Suppose that the memory fits. We have studied using all the tricks that we use. We have BF16, we used gradient checkpointing, and we made the model fit in the VRAM, in the memory of the GPU. How can we make it faster? Why is model training still taking days, weeks, even months on smaller GPUs? Like we just answered a question, that modern GPUs are created with compute in mind. Often the real bottleneck is memory, data movement. The arithmetic units that we have sit idle waiting for data to arrive. Often the operating on it or computing maths or doing floating point operations is cheaper or faster than actually transferring the data from GPU memory from kernels to kernels. It's very simple to consider that if every single time we have to do like an addition or a multiplication, we take two numbers, we run to an operation center, we do it, and we come back. That's one trip for every single operation. This becomes ineffective when the trips are the bottleneck, when moving memory from one location to another due to the architecture that we use. When that is costly, then this becomes a problematic procedure. This is why a lot of efforts in creating kernels, which is sort of the bridge between high level software that we write and the hardware that is running, like GPUs. A lot of the efforts is made into fusing kernels, where we can do a lot of different operations in fewer trips. Imagine if you, instead of taking one trip per operation, you can take one trip per 5 operations or 6 operations. This is known as batching, prefetching, or profiling as well, where we are able to maintain the arithmetic units, where we are able to maintain operations as fast as possible by limiting the data movement bottleneck. This is done by a lot of different things, but one of the things we'll study today is something known as torch.compile. Torch.compile is a framework provided by Torch, which is PyTorch. It's a very common deep learning library used for all sorts of deep learning. It's very widely used in industry and LLM training as well. What it does is it fuses kernels. What that means is normally eager PyTorch, which means simple PyTorch, would launch one GPU kernel per operation for every single floating point operation, which really means just multiplying or adding two floating point numbers. It would launch one GPU kernel. That would cause the launching, creating, closing, and transferring of data from GPU kernels the bottleneck, and pays the Python overhead for this. This is why data movement, the bottleneck that is created by data movement, is felt so fiercely, especially when using Python, which is historically not a very fast language. What torch.compile does is it traces the graph ahead of time. Torch is on its own built on top of C++. So it's using the leverage of a faster language, and it creates something known as ahead of time compilation. What it does is when you have a computation graph is done, or a graph before, not even the backward graph that we studied for AutoGrad, but a forward graph where you have the path that an input will follow, what functions will operate on it. It compiles the graph ahead of time and fuses the operations which can be fused together to create many small operations into larger fused kernels. What this means is, for example, if our graph had the input being multiplied by a number, added to a number, then multiplied again, then added again, and then outputted, what it would do is it would trace this ahead of time before any actual operation is done on the input. It would trace the path that the input is about to follow, and it would create a fused kernel, as in it would probably compile both of the multiplication operations into one kernel and both of the addition operations into one kernel, for example, obviously. And it would create both of those kernels fused, so that the creation of the kernels and transferring of those variables, of that numbers, the data into those kernels would have to happen fewer times, fewer trips, larger fused kernels. It's very simple operation that is handled itself by torch or compile. We can see that this intuitively can understand this and mathematically as well, that this adds nothing to the cost line. It neither adds nothing nor removes anything. We are not reducing compute, still the same number of operations have to happen. Neither are we reducing memory. We still have to store the same amount of numbers. It's just the transferring of those numbers from one location to another is done fewer times so as to make the operations faster. In the best case scenario, we are able to save around 1.5 to 2 times the operations using torch.compile. 1.5 to 2 times the time for operations. In practice, this number is slower because, again, the more complicated a computational graph becomes, the tougher it is to fuse kernels. But torch.compile is a very powerful tool for making any forward pass, for making any deep learning model with a lot of different functions, making it run faster by fusing kernels. Again, this might seem sort of alienated because we don't properly might not understand what kernels are or these operations are. But I would encourage you to sit and wait. The rest of the lectures will explain a lot of the portions missing here. And also, you can conduct a lot of independent study and try to understand what these mean, or you can raise questions to us further on. I think, Venkat, we can take a break now.
Yeah, I think we are right at 1 hour 15 minutes. I think we can shortly go for a break. So as a speaker, like, would you like to give like 5 minutes or 10 minutes, depending upon the content that you want to deliver after that? I know that we will have roughly about 35 minutes probably after this. Roughly
Sure.
25 minutes for the questions for 10 minutes.
Yeah, so I think since we had the question discussion as well, we can go ahead with a 5-minute break.
5-minute break, okay. Hey, so now it's 9:45. Oh, sorry, 7:15 India time. So probably we'll resume back at 7:20. Is it all okay?
Absolutely.
Okay, you can leave the floor. I'll just pause the recording for 5 minutes and then we can resume the recording back. Thank you.
Sure. So I'll continue. Yeah. Like we discussed, right now we're considering efforts to make LLM training and all deep learning in general faster. We considered something called torch.compile, which does ahead of time fusing of kernels to make operations faster while considering the memory bottleneck of transferring data. So this again considers the way that modern GPUs are designed. It was a very good question that was asked before. And we are able to fuse a lot of kernels together to preserve the number of times that we transfer data from each different point in the graph from each different kernel. We're able to reduce that to prioritize speed and prioritize the operation of the GPU in mathematical sense. There's a lot of different things that are also done in industry. A lot of times one GPU isn't enough. I'll be giving a very quick overview. There'll be a lecture taken further, which will cover a lot of these things, data parallelism, tensor parallelism, and pipeline parallelism. But sort of a quick overview says that when one GPU isn't enough, we tend to have to use multiple GPUs. The question then arises, how are we parallelizing the operations across each GPU? One simple solution is we put the same model on each GPU, train small slices of data on each of them and reconcile at a certain point. So another one, this one is data parallelism. Another one is tensor parallelism, where we split one single layer across GPUs and where one layer alone will not fit because of memory restrictions. And third is pipeline. Obviously, we split the stack of layers across GPUs. We put certain layers on one GPU and certain layers on another, and we do sort of a like assembly line again, where each GPU feeds into the other. Again, this will be covered further in one of the lectures, but it's very important to understand what the motivation behind data parallelism and multi-GPU systems are, which is again the bottleneck. Either a memory is not being able, like the memory requirements of a model are too large for one GPU to store, or it simply isn't fast enough for it to be feasible to run on one GPU. Very importantly, we've studied something known as the cost line the entire lecture. But what we haven't considered is, what does this cost line mean in practice? It's we have had no mathematical basis for extending the cost line. We're done it purely qualitatively. But understanding quantitatively is very important when considering the economics of what is the model that we're building, what is the hardware that we require, and what is the kind of data that we need. How can we build the cost line in real life? There are a lot of different metrics, a lot of different measures when studying LLMs, and there'll be a lot of different ones considered throughout the rest of this course as well. But three main ones that we can introduce simply is tokens per second, which means how many tokens are being processed per second by the model. Tokens will be explored in depth in the next session and in a few sessions of further. GPU utilization and VRAM, these are numbers that we very often see on Activity Monitor or Task Manager on our laptops. What this means is how much of the GPU is actually being utilized and how much of the GPU's VRAM is actually full. This makes us understand, is the GPU idle? Is it actually operating? And how much of the data is actually being stored in VRAM? Latency and throughput. Latency is basically how much time it takes from an input to an output, or any given portion, how much time that portion takes to operate. And throughput, like we studied before, is the operations happening in the interior of the model. All of these combined in a certain measure can help us create this cost line, visualize qualitatively and quantitatively when actually training SLMs. We can also consider something known as like you often see these graphs in task managers or any of these server standpoints or stuff like that, where this is just simply GPU utilization. We studied a lot of different things known as profiling in Torch or Compile as well, how we're able to fuse kernels together to reduce the number of times we have to transfer data from kernels and increase the amount of time actually spent operating on the models. This is very quick, easily visualized on this sort of graph, which shows the GPU utilization. As written normally, we get around 30% utilization. As you can see, the orange graph on mean gets around 30% utilized. On a profiled run, we get up to 90% on mean. The small dips you see are when a new kernel actually has to be created, when the operations actually have to travel, or the data has to be moved from one place to another. The longer we can spend on the operating procedure, the more that we can actually use the GPU. This creates almost 30%, 3 times better the GPU utilization using profiling. This again translates directly, if we're able to utilize the GPU 3 times better, then we're able to do it 3 times faster, and hence we can run 3 times more experiments. This simply means that this signifies to us that if our GPU is idle, if the utilization is low, then we're setting our money on fire. Then we're not properly utilizing our GPU, and hence we're not properly putting all of our resources where they should be. There's another very important cost that is very widely considered in certain spaces, but sort of dismissed in others. It's not just running the model that has a price, but so does building the things. Right now, what we studied, everything is quite theoretical. We've considered a lot of a lot of tricks, a lot of hacks on how to make models smaller, cheaper, faster. But all of these actually have to be implemented. All of the different portions of a model have to be implemented in code. Data processing, data travel, operating on each of them, training, pre-training, post-training, data parallelism, all of these things need to be actually implemented in code. And creating those code bases, creating those frameworks is also a computational overhead that must be considered. Operational overhead that must be considered. Here comes in OLM. OLM is an open source library that is designed specifically to be PyTorch for LLMs. It is built on top of PyTorch and is cross-compatible with every single PyTorch ability. And actually, I was one of the people who worked on OLM, and we made it with the vision of making LLM training simpler, easier to read, but also easier to experiment with. Today, we set up a lot of different things like checkpointing, BF16, autograd, torch.compile, all of these things. In a world where we have to use PyTorch for a lot of them, and we will explore this in the live demonstration, writing all of these in code, making sure they work, making sure they wire correctly is a challenge on its own. OLM, which stands for Open Language Model, sets all of these things up very simply. it sets all of these things up easily for you to understand, where you can read them almost as English, and you don't have to keep re-implementing all of these things together. It has a lot of different operations, like you can put in a lot of blocks together in a composable manner. There's a training loop that you can create very simply with mixed precision built in, with tokenizers built in, with data sets, data loaders, everything built in. There's a lot of different model families which are pre-implemented. So if you don't want to define the architecture yourself, you can use a predefined architecture that the library provides, and it is completely compute optimized. So you don't have to rebuild all the tricks here. It utilizes as much of the hardware that you're giving it that any other framework can. It is almost 92% compute effective as compared to PyTorch. You can see the cost sign reduces on a different axis. It is not reducing the budget. It is not making saving compute or memory, but it's a different axis. It represents ease of using and saving that budget. It makes creating these softwares, writing the code for this, and creating these models much simpler. We'll see a further demonstration actually in the live demonstration. So we'll walk through that and understand how OLM helps in a lot of different aspects, not in just creating all of these hacks, but also in training full end-to-end LLMs. So now I'd want to dive into the live demonstration. I'll set up, I'll just showcase the notebook, and we'll dive into all of the tricks and all of the things that we discovered in theory, and we'll understand how they're actually done in practice. Just one second. Is it visible?
Yes.
Yes.
Okay, great. So this entire notebook will dive into 7 sections. One very similarly arranged to the rest of the model, rest of the lecture itself. We'll first learn AutoGrad, how the graph gets built. If whether you ask for it or not, every operation creates a graph. Then how learning happens, and what is the memory that this graph quietly demands. Then we'll introduce OLM at this stage, and we'll introduce why it helps, why it's better, and why it's easier to use. And obviously, we'll sort of create an encouragement to use LM, but of course, for the rest of this lecture series, you are free to use any framework you want, but we would just like to introduce something that we think makes creating these SLMs much simpler. Then we'll go into the first cut, bfloat 16, second cut, which is gradient checkpointing. We'll study torch.compile, see if it makes things actually simpler or faster. And we'll put it all together to show you how OLM is used to create an actual training ground without diving into any of the actual deep technical transformer topics, which will go on further in the lecture series. So what we can do is we'll sort of run a few basic lines. We'll try to understand, we'll install open language model. And this is Google Colab, so there should be a GPU available, which should be Tensor T4. Let's quickly wait for that to pop up. Yes, so we have the Tesla T4 GPU available. Okay, so like we considered in the lecture series, a network is just composed functions. When you do a lot of operations on functions, this creates a network. The moment a tensor is marked, requires grad is true. This is all PyTorch notification. I'm so sorry for missing that out. We'll be using PyTorch and OLM in this live demonstration. So as you can see, we create a random variable. What torch.randn does is creates a random variable of 4x4. What requires grad equals true does is this attaches this variable to the graph. Any operation that is done on this will hence create a graph going forward. Like we see, we create another variable y, which is just twice into the variable x. But since this variable x is attached to the graph, this y will be attached as well. Similarly, z, which is the sum of y, will be attached as well. We can see the outputs of this, that each of them has something known as a grad fn. Y.grad fn and Z.grad fn. This graph node recording, this came from a multiplier, also known as a gradient function. What function was operated on any variable to create this? Hence, we can do a derivative of this function when needing to calculate the gradients for this. When we do z dot backward, we're able to see that the gradient of x is dz by dx, computed via one backward walk. What z dot backward does, if you are unfamiliar with this, is it does a backward walk of the AutoGrad graph that we studied. This is where the gradient descent actually happens. This and the optimizer stepping. What it does is it walks back from the gradient from the graph starting from Z. It walks it back and it creates gradients for each of the variables based on the grad fn's that is defined up here. We can see that even though we did backward on Z, the x function, which is the original function, has now received a gradient because the entire graph was stepped back. Another thing very important to consider, that the instant one backward is performed, the entire graph is toned down because one backward pass is complete. Hence, the entire x, y, and z have received their gradients. Hence, there is no necessity for the same computational graph to be stored again. If we keep storing this computational graph, that might create problems when running multiple forward and backward passes, where old stale computational graphs are still stored. So if you see that if we try to run z backward again, it will create a runtime error. Let's try to expand this to a larger system. Right now we just had two functions. One is times 2 and one is a sum. What we have here is how a very modern neural network is established in PyTorch. If you're very unfamiliar with this notation, that's completely understandable. What we're doing here is describing an nn.linear. nn.linear is very simply a weight matrix. That's all it is. A weight matrix of dimension dim by dim, which we've defined as 16. We have created 3 of these in this one class, and we perform a forward function by creating again, like we considered, a composition of functions. We first perform a weight matrix multiplication on this x. Then we perform ReLU on it, which is known as an activation function, to limit the output of this weight matrix. Similarly, so on and so forth for F1, F2, and F3 gives a simple output. This model defines a very simple chain where input is operated on by several different functions, very similar to how an actual neural network operates. We create a simple input, which is a random from of dimensions 8 and 16. We attach it to the graph, and we put it on the GPU device that we discovered. Then we apply the chain on it. What this will do is that it will create the graph for each of the variables. Each F1, F2, and F3 will now have their own grad Fn. And we can see this visibly. That we are able to see that there's an accumulate grad and backward object on each of the gradient functions. Here we can see for an actual network how the computational graph is created. Moving ahead, like we discovered, how actually does memory operations occur? How does the learning operations occur, and what is the memory that the graph demands? To compute the gradient, the PyTorch needs the actual value of x from the forward pass, not just the graph shape, right, that we consider. So what we do is something known as, we'll study something known, the eager PyTorch determination, which is the one without checkpointing. What we'll simply do is, this is a lot of different lines of code to understand what is the memory being stored for activations. Here we'll try to get the answer in megabytes, and we'll use 256 dimensions, 100 layers, and 4096 as a batch size. And what we'll do is we'll run and measure on a simple random input of a model with the 1024 dimension and 40 depth. Sorry, I'm so sorry, 256 dimension and 100 depth. So this is creating a very similar network to what we observed before, but on a larger scale, since we want to observe the numbers changing at an actual value. This shows that without checkpointing, without doing the trick that we just observed, all activations have a memory of 977.5 megabytes for this hyperparameters. The model just creating on the backward pass for AutoGrad is storing 977.5 megabytes in activations. We'll study the operation of checkpointing later, but first we'll introduce something known. We'll introduce OLM. OLM is a library that like I discussed before, that makes writing this code easier. For a very simple example, what we'll do is we'll create something known as a llama style transformer block. Again, all of this will be explained further. Most of these lines of code and these statements should raise more questions, so that when these questions are finally answered, you'll bring back the intuition that we're establishing today. But just understanding from a simple perspective, creating a transformer block, which is one layer of a transformer, which is one portion of an LLM. So one small portion of an LLM is written like this in PyTorch. It requires a lot of different operations that we need to define ourselves, because a lot of different operations are not implemented. There's been a lot of different researchers and a lot of different research being done into creating newer and better elements in large language modeling, in small language modeling, in language modeling in general. Even for knowledge graphs, symbolic approaches, there's a lot of research being done currently, which creates a lot of which comes up with a lot of different architectures, solutions, operations, models live. PyTorch rarely covers all of these things natively. When implementing something that is newly been created, like grouped query attention, for example, again, which will be covered later, this isn't natively supported in PyTorch. You'll have to write the model yourself, which is a lot of different lines of code, a lot of different wirings that you have to put together. Similarly with rope, which is rotatory positional embeddings, again, something that will be covered later. But a lot of these things are new inventions that researchers have come up with to make language modeling better, which aren't locally supported in PyTorch. Implementing the same exact model in OLM requires only these lines of code, because OLM principally supports all different components that are being put out uh, by researchers, by companies to make operations. To build an OLM block is very simple. It's almost English on its own. You can just return nested blocks, whereas a block contains one layer of RMS norm, one layer of group query attention, then another layer of RMS norm and swiggle. Again, most of these things will be defined later, but the intuition is of using this library is that writing the code for it will become much, much simpler. We'll also see how data operations, training, and parallelism become much easier using OLM further on. So using this library that we've just established makes writing the code easier. Let's do the first cut. Let's apply Brainforce 16 mixed precision. Like we studied, the exponent is the range and the mantis has the precision. The BF16 keeps the zoom, keeps the exponent while reducing on the mantissa. Similarly, very simply what we're doing is we're creating the same model in OLM, which is a very simple language model. Again, the architecture of this will be defined later. We create the same language model. One model is an FP32 by default, and the other model, we are specifying that the data type is torch.bfloat16. Then what we're doing is measuring the memory, measuring how much does it actually take to store the model on device. As you can see, by simply natively, we are able to store the BF16 costs only 34.8 megabytes, where FP32 costs 69.6 megabytes. That's a ratio of 2 times. We're able to save 2 times the memory. Again, this is sort of naive because we are entirely porting every single data type to data point to bfloat16. And since bfloat16 is mathematically half the bits as FP32, this is to be expected. In practice, when using mixed precision of larger models, we'll probably observe this number be closer to somewhere 1.3, 1.4, but it's easy enough to understand how this saving happens. As you can see that autocast, this is a very quick example of mixed precision. Torch.autocast is a framework given by PyTorch to create to enable automatic mixed precision, where the model itself, where PyTorch itself is automatically able to prescribe where bfloat16 is needed and where FP32 is needed. What it does is, when you do with torch or autocast enabled, even if you run an FP32 model, it will create the data type to bfloat16 when necessary. As you can see, even though this is the FP32 model, and but it is run under torch or autocast, the output has the data type of bfloat16, and the logis.shape is unchanged. So we are able to operate at the same outputs while using automatic mixed precision powered by torch.autocast. Let's now apply the second cut, which is gradient checkpointing. Like we studied, we have to, when creating a computational graph, we have to store all the activations, which simply isn't feasible from a memory standpoint. Like we considered, as the model scales, this number will get exponentially larger. And then further and further, this might become the bottleneck, which may stop us from training models. So what we'll do is something known as gradient checkpointing, which we studied before. Let's see a very simple explanation of this using PyTorch. We'll manually write it ourselves to understand how it works. Torch.utils.checkpoint is a call that stores an activation checkpoint on the graph. It has been provided by PyTorch. It's implemented already. So what we do is we define something known as segment. This is the nth activation we were talking about, sort of at a larger sense, where the nth layer's activation is stored. Right now we define a segment.4, a segment as 4, right? Again, this established a very similar network that we studied before, a chain of layers for a certain depth, where each layer has a certain is just a matrix of a certain size. What we'll do is we'll run each of these layers separately, checkpoint each of the layers run, and then run the rest of the layers. So for every fourth layer, we are running torch.checkpoint. Sorry, torch.utils.checkpoint. This stores the checkpoints for a certain nth amount of layers, so we can actually perform the cut that we're trying to do. We'll define this model. We'll take a very simple input, a very random input, again, by a batch and a dimension, very similar to what we did above here when we were studying the memory that it takes. Sorry. Yeah. We defined a torch.random variable, we did an output, and we measured how much memory is it storing. Using the exact same values and exact same data, just now doing gradient checkpointing, we'll try to understand how much memory are we actually using now and what is the save. We can see that using torch.checkpoint, torch.utils.checkpoint, and using gradient checkpointing every 4 layers, that the peak memory that we are using is only 701.9 megabytes. This is a memory reduction of almost 1.4 times. This is done on an actual model with actual dimensions that are used in practice. So we can see that we are able to reduce memory in practice using gradient checkpointing. This is very widely used in a lot of methods where the model's memory requirements far exceed what we can actually store on GPU VRAMs. Often the models that we use, GPUs that we use, like H100s, etc., have 80, 90 gigabytes of memory. Models often themselves, the activations themselves go up to 200, 300 gigabytes, which simply isn't feasible. What we do then is this gradient checkpointing. We reduce the amount of memory that is used by a certain factor using gradient checkpointing. Let's now go on to the faster portion that we did, where we establish torch.compile. What torch.compile does is it automatically fuses kernels, like we discussed before. This is a very simple function that measures the time steps that it takes for a model to run for n amount of steps, which we've defined arbitrarily as 100. We'll build a very eager model and we'll figure out how much time it takes to run normally without torch.compile. Then we'll try to run torch.compile on it and try to understand how much time is it actually taking. An important thing to consider is something known as warm-up. Torch.compile requires a few forward and backward passes to be warmed up for it to understand what operations can be fused together. Once those are done, then it reaches peak performance.
Keshav, just a reminder that we have 14 minutes left in the session.
Yes.
Just letting you know.
Absolutely. Thank you. Thank you so much. Yeah, we'll just about to close the live demonstration, then we'll move to discussion. Yeah. As we can see that the eager one uses, so let's run this live. It'll take a few seconds. 1 second. Yeah, so I'll share this notebook. I think it'll take a few minutes to run, but using torch.compile with this simple model, we're able to save around 1.5 to 1.5x time, because this model, when we do torch.compile, is able to fuse a lot of the kernels together, fuse a lot of the operations that are done, like the model that we defined up here as a lot of different weight matrix multiplications, additions, and torch.relu. What torch.compile might do is combine a lot of these operations together into one trip to the GPU. This would save time, and this is very often commonly used when trying to make models run faster when this is feasible, obviously. This is putting it all together, a very simple OLM training run. This is very few lines of code to understand how OLM works. It's very simple. What we do is we load a data set, we create a data loader, we create a model, an optimizer, and a trainer. Then what we do is we do trainer.train for a specific amount of epochs and for a specific amount of max steps. This creates making training pipelines in code much, much simpler. What this does is it builds on top of PyTorch, and it gives functions like local data set, local text data set, data loader, trainer, and this LM data set that we created. And it gives you an opportunity to experiment with a lot of different architectures or create training runs very easily. So this sort of puts together everything that we studied, everything that we studied in theory, in practice. It showed all the different cuts that we created and all the different factors that we studied, and also how OLM wraps everything together neatly. A very a good exercise that you can take for yourself for this week would be trying to apply gradient checkpointing to the OLM model. The OLM model natively, some models do already do gradient checkpointing as is prescribed, but writing explicitly gradient checkpointing, very similar to how we wrote here for Torch, would gradient checkpointing very similarly wrote for PyTorch. Writing this for OLM will help you understand how both of the cuts work and how both the libraries work. So this has been a live demonstration of all the different things that we studied. That sort of covers what we wanted to cover for this lecture. I'll just give me 1 second. Yeah. So that covers 90% of what that covers almost entirely what we were hoping to cover for this lecture series. We have focused on how to make focused, cheaper, and better models, and built a perspective on how to approach SLM model training. This lecture should leave you with a different perspective on how to approach the rest of the lectures. How to think about what is the memory that each thing that we're doing costing, what is the compute we're costing, why was it done in certain ways, and how will I implement it in code? How is it applied to the SLM principle? So for a discussion question, of course, we'll take questions as well, that I wanted to raise to people is we studied a lot of different things of how we can save compute, how memory and compute is a problem. The discussion question that I wanted to pose to you is, what if compute and memory were free? Would we still build specialized smaller models, or would we still build SLMs? And that's sort of the question I want you guys to take away with, to figure out the reasons to build SLMs that survives free compute and memory. What if compute and memory were never the bottleneck? Why would we still build SLMs? So that's something that we can discuss on. And obviously, we'll share the related materials using slides and code and all of this stuff on the Discord. So now I think we have around 10 minutes for questions and on the discussion topic or in general. Right, Venkat?
Yeah. Before that, I mean, I know that Keshav have touched the surface in this first lecture because it's all about course introduction for deep learning, PyTorch, and so on. And a lot of the next few lectures that we'll cover those topics in depth. And so do not worry about that. You do not get everything out of this lecture because it is just the fundamentals here. But we will go deep in the topics in the future lectures there. And I think Keshav also mentioned that he'll be sharing this notebook. So there will be a link in the Discord. Rajvi from our team will be posting that link. And then that will be a Google Drive. And you can access this notebook and you can play around with this notebook. It will be a read-only access. Make a copy of it and play around with it in your Google Colab or any other environment you're interested in. And last thing that I want to share is that Rajvi also shared a feedback link. Please take a moment to fill that feedback form when you get a chance, which will be very helpful for us to plan our next sessions and also address any issues in the current session there. With that, I will open the floor for questions.
I will also like, you can stop the sharing. And I'd like everybody to turn on their video, and maybe Raju, you can capture, what the class looks like, right? I mean, we should not have the interactivity of a real classroom as opposed to just this virtual thing where, yeah, come together, ask questions, participate.
Sure. And Keshav, if you can just go and stop your screen share, so that will help us to take a screenshot as well as have more interactive discussion.
Yeah,
sure.
So questions, guys?
Sir, I have a question regarding what is the smallest size in terms of maybe documents or data or tokens that can be used to train a meaningful small language model?
What is the smallest activity you can think of? What is the most narrow, most limited activity you can think of? So I think you need to be mostly driven by how can you think of a tiny little function that is useful enough to be able to and to be able to code up as a model. Maybe you have one question. Maybe you can think of a, let's say, a task like take a photograph with your smartphone of what you are about to eat, and assume that the model knows your healthcare requirements or limitations, like you have diabetes or blood pressure, and it tells you should you eat this or not. But think about something very targeted and very small. Then see if you can create a model for that. But keep in mind that a lot of power in the traditional language models comes from the size, right? So understand that so much of the science has gone in developing large language model, so much of the engineering has gone in developing large language model, where the mantra is that the larger the amount of data, the smarter your model, right? More capable the model. Now, we are trying to now flip this on the head and trying to say, what is the critical task to be done? And can we create a satik? Can we create extremely targeted model that is highly accurate, very good at that specific task, but doesn't know anything about other things, right? So with going for that, then you have a wide variety of options. One thing that we did not discuss today at all is the role of knowledge. So in the last century, previous century, we are building expert systems by writing the rules, right? And today that is what we consider trivial. But the point is that some tasks can be deterministically solved by just a few rules, right? Then there may be a task that human may be performing in the real world that have a few rule of thumb, and they get that job done very well. So what happens is that as you use more and more relevant knowledge, the amount of raw data needed to train the model reduces. And that is where this so-called neurosymbolic comes up, right? Where you are combining the power of data and knowledge. And that changes the equation completely. So you would not today, you can't go and look at the literature and understand how would you answer this kind of question, because the literature and current technology does not adequately exploit the knowledge aspects of it, right? So suppose you ask, suppose you present a complex data to a very good expert in that field, and that expert only looks at just a little part of it and hones into that and tells you it is not everything and so on and so forth. The expert knows just what is the relevant thing here, what is the deciding factor. Now, in this kind of thing is just not done by current technologies, right? So I think the field is changing. This, my team has done very large amount of work in neurosymbolic AI. As I said, multiple dissertations have gone on, but and we have learned quite a bit, but there is a lot more to go. And the big players are just starting to exploit that. So Claude started to exploit structured data or knowledge. When you see Perplexity or Claude creating a specialized products for, let's say, finance or stock picking, then what happens is that um, um, they end up using stock market data, let's say, right? Very concrete data. They end up using the knowledge that have been derived over a long period of time as to under high interest rate environment, bonds perform better than stocks, things of that nature. Under low, easy monetary policing, stock perform better than bonds, right? These are the examples of the knowledge, right? So, so that changes the entire thing. And largely, the large language models have not been exploiting that, but now they are figuring out. And now they have started to exploit this. And some of us who have been working on ontologies in knowledge graph, hey, Soumyadeep Nag, you need to do something because you know, coming up for at the time. So fix your network exposure to you. Earlier at the starting point, I showed you the link to the neurosymbolic AI, right? If you are curious, go ahead and browse through that. There are many tutorials, there are many labs, all that are there. You can learn a lot on your own and get appreciation for that. But that changes the whole equation. And you'll learn something about it. And that's why this course is, this bootcamp is not limited to just so-called standard SLM. Standard SLM, they don't use knowledge. They are only using, they are only reducing a large model and with many pyramids into a small model, relatively with small parameters. Let's say a 5 model with 7 billion parameter. But that has not exploited the use of knowledge, for example. So a lot of space is unexplored yet. But the important thing for you guys, you guys are selected few because you are nominated, most of you are nominated by your institution. Important thing for you is to look at the opportunities that have not been yet explored very much by the people. I'll give you one very interesting example. In 2017, I was asked to give a keynote in China, in Chengdu. And in front of me were 600 plus people. They were learning about knowledge graph in 2017 in mass level. And neither US nor India was doing anything in that area. The point here is that you need to figure out the unexplored trend and see how you can get deep into that and then how you can do things that others can't. What is it that you have that others don't? That is where the trick is. Okay, next question.
So there is another question in the chat line. When do we need SLMs? When can we just use either an LLM or any third-party applications? For example, if you take document extraction, we can use LLMs for the same. We can use something like a third-party provider like Azure for the same, or we can build an SLM for it. So for every use case, how do we know when it is economically beneficial to build an SLM?
Yeah, that's a good question, but in a way, this is not too difficult a question to answer. I don't know what I was trying to say. Yeah, so what happens is that LLMs come up with certain advantage. The answers look human-like and very, very because it combines data from many sources. It looks very appealing, but in reality, it can be far from appealing, right? Because you guys know that LLMs make up, references, right? They may come up with the title and authors, but nobody by that name might have published that paper, right? So this is a problem. So one important thing is, what is it that this class of new models do that LLMs can't do? So there are a whole bunch of articles that are written to explain this. Let me see if I can show you one of them. The article I'm trying to show you, let's see if it shows up. Huh. So in explainability is a very important problem. But the general statistical approach for explainability in use can explain only based on the data and based on the statistics or the algorithmic aspects of the computation. It doesn't explain things based on what is a knowledge in that particular domain. Let's say clinical knowledge, let's say medical knowledge, right? So what happens is that look at this particular picture, and it's very interesting if you think about it. Ask yourself, how do you understand the language? Like I'm talking to you, right? There is a lot of thing going on in human brain. You have understanding of syntax and grammar, so you have lexical knowledge. Right? All of you have that. You learned grammar, right? You know what the punctuation at a particular point means. You have linguistic knowledge, right? Like what you might have in WordNet. You have common sense knowledge, right? I mean, you know that Gandhinagar is the capital of Gujarat, right? There is a broad-based general knowledge. Sorry, no. So the broad-based general knowledge will be this Gandhinagar is a capital knowledge. Common sense knowledge. You take a glass filled with water and turn upside down, and the water will flow out, right? That's an example of common sense knowledge. And then you have domain specific knowledge. So if you are doing clinical work and you are a doctor, you have very specialized knowledge about clinical and medical concepts. If you are a worker in a automated plant where much of the work is done by robots, and you have specialized knowledge about where robots typically fail and how do you fix that problem, right? Now ask yourself, does a large language model has understanding of all of this? Compare the complexity of a human effort in understanding language involving all this knowledge. You can't argue that any one of this is not needed. They all are needed. And yet, do knowledge graphs have all this? Were they trained on all this? No, they were not, right? This is just one example of it. But beyond that, let's say important issue like alignment. So you have financial regulation. You have a regulation in pharmaceutical industry, right? Like FDA regulation. Now, for all these, how would you make the large language model compliant with all of those things? Suppose you use large language models, but it does not give you a guarantee that it complies with the regulation. You are in trouble. So the kind of model that we are talking about here, custom compact neurosymbolic, are the ones that really do very different thing. So they are not just the SLMs, small language models, equivalent of smaller version of large models. That is one. But they are also highly specialized. And because of their specialization involving use of knowledge and many other things, they solve several problems very well. So here is that picture. For example, causality. This is a very complex topic. For example, reasoning. The LRM, language reasoning models, are only doing a small fraction of the problems that, of the reasoning that there is to be done. They are largely based on statistics and syntax, and they don't do reasoning. We have an application, Nourish, for food nutrition kind of stuff. It uses 6 or 8 knowledge graph, different kinds of knowledge. It would have a knowledge about the connection between high salt food and blood pressure, right? or it would have knowledge about use of refined sugar and and diabetes, right? It will also have knowledge of the how the food changes by different cooking method. If you take if you do deep fry, you might have trans fat, which will be very bad for your heart and cholesterol. But if you broil it or if you bake it, you might get much better results. And so for certain health conditions, those will be very good. How would effectively, how would you use that kind of variety of knowledge to effectively reason? That's the kind of thing that you can do in this new class of models. LLMs and LRMs don't do that. Right? There are many registered cases and court cases where people have used ChatGPT and teenagers have done suicide, and that still continues to happen. It's just that they are so big that they can fight those cases. Those cases. But we want to create models that would not harm any human. So for that safety, you need to make a very specialized or custom models, and you need to test all of them. So we have created a new class of sovereign AI, a small model or custom model development, which has data component, knowledge component, training component, neurosymbolic training component. It has evaluation component. It will evaluate with regards to that particular application in healthcare or nutrition or a factory floor or semiconductor fab. And it has a composite part, meaning it can have an agent that uses large language model to improve, to implement a co-pilot or implement a chatbot, but its core decision making is done by as a small model, custom model, right? So what I want to impress upon you for now is that this whole field of AI models, and I want to emphasize that you should not only limit yourself to language models, because there are a lot of things in the world that has nothing to do with language. When I'm doing solar power plant maintenance, when I'm doing semiconductor fab maintenance, there is no language per se. There are sensor data, there are images, there are video captures, there are robot created data that are passed on, right? So these are models that are not exploiting a language. In fact, there is a fantastic body of work that is just emerging, saying that human reasoning is not language based. They have parallel reasoning in non-language part of it. So this large language model people falsely argued that they are bringing intelligence and reasoning by being very good at language manipulation and understanding. In reality, increasingly, we understand that human brain does not reason and think in language terms. It is one of the many modalities that we use as human. So you guys should think about, there'll be increasing use of non-language model AI models. There'll be increasing use of model for just a specialized thing. None of the public company can use any model using a large model using API, because the regulatory body prohibits from putting their data online. They have to have air gap model. So what would happen is that a lot of jobs in next 2, 3, 4 years will be in the kind of things you're going to learn in this bootcamp, well beyond what you learn in large language models or even small language model course on YouTube. Okay, I hope that is exciting. I don't know if you want to continue this, but anyway, I'll stop here.
Thank you, Dr. Sheth. Thank you so much for staying extra 12 minutes in the session. I know that's very interesting, intriguing, and thank you so much for staying late. And so we'll continue in tomorrow's session, which is day 2. And Yeah, if any questions unanswered, will be like, don't worry about it. We will take all these questions, collate it, and then answer them in the Discord invite as well. So
Yeah,
thank you.
just take your question, take
Sure.
your questions and put up on Discord and continue the conversation. And you're
Absolutely.
most welcome. Even if you are an attendee, if you have an idea, I encourage you to give reference and participate in discussion and bring your ideas out. So it's very important for you to be able to learn and express and discuss. Okay. All right. Goodbye.
Thanks, everyone. Have a good day.